US Physics Olympiad, year 2022. F equal MA, exam A. This year was split by two equal competitions, and students could participate in any of them. As usual, it was given 75 minutes for 25 problems. If you want to get more interesting problems, subscribe for this channel, please. Problem number 1. A projectile is thrown upward with a speed v. By the time its speed has decreased to v over 2, it has risen height h. Neglecting air resistance, what is the maximum height reached by the projectile? Solution for problem number 1. Here we can use regular kinematic formula for height. Height y equal initial speed square minus final speed square divided by 2g. And in first case we have initial speed is v and final speed is v over 2. So h equal 3 over 8 v square over g. And to count what is maximum height, we can use formula big H equal v square minus 0 over 2g, which is 1/2 v square over g. And this is 4h over 3, which is answer B, and that was solution for problem number 1. Problem number 2. A car is moving at 60 miles per hour. When the drivers notice an obstacle ahead, hitting the brakes, the driver decelerates at a constant rate and manages to come to a stop just barely before hitting the obstacle. If the car had instead been moving at 70 miles per hour and started decelerating at the same place and at the same rate, with what speed would it have hit the obstacle? Solution for problem number 2. Here we can use the same kinematic equation in both cases. We have final speed square equal initial speed square minus 2 decelerations multiplied by distance. In first case we have 0 equal 60 miles per hour square minus 2ad, and in second case we have v final square equal 70 square minus 2ad. Now we can subtract from third equation second equation and find that v final square in second case equal 70 square minus 60 square, which is 1300, and the final speed equal 36 miles per hour. This is answer D, and that was solution for problem number 2. Problem number 3. Two blocks of mass m have an inelastic one-dimensional collision. Initially, the first block is moving with the speed 5 meters per second, and the second is at rest. After the collision, the first block is moving with the speed 2 meters per second. What percentage of the system's original kinetic energy was lost during the collision? Solution for problem number 3. We have initial speed of the first block is 5 meters per second, final speed of the first block is 2 meters per second, and because of momentum conservation we have final speed of the second block is v0 minus v1, which is 3 meters per second. Now let's count kinetic energy before collision and after collision. That will be k1 and k2. Now let's count what is the relation between them. That will be k2 over k1, which is about 0.52. This is energy what was saved, but we have to find what is energy lost. That will be 1 minus 0.52 or 48%. This is answer C, and that was solution for problem number 3. Problem number 4. A mass on an ideal pendulum is released from rest at point 1. It swings over to point 2, at which point the string suddenly breaks. Which of the following shows the trajectory of the mass? Solution for problem number 4. When the string breaks, the mass has zero velocity by energy conservation, so it just falls straight down. And thus the answer is B, and that was solution for problem number 4. Problem number 5. A uniform solid ball with mass m equal 1 kg and radius equal 10 centimeters rolls without slipping on a horizontal plane so that its center of mass has velocity v equal 1 meters per second. What is the ball's total kinetic energy? Solution for problem number 5. Total kinetic energy equal translational kinetic energy plus rotational kinetic energy. Here I its moment of inertia for solid ball, that's equal to 2 over 5 mr square, and the angular velocity omega equal v over r for motion without slipping. So total energy equal this expression, or 0.7 joules. That's answer C, and that was solution for problem number 5. Problem number 6. A bulb of mass m hangs from a rigid massless rod forming an ideal pendulum. The rod is held horizontally and released from rest. What is its maximum tension during its swing? Solution for problem number 6. First, let's draw the picture. During the motion of this pendulum, we have two accelerations. One is tangential, and other, which is important in this problem, is normal acceleration. Let's write the equation for this acceleration. We have mass multiplied by this normal acceleration created by tension of this rod and part of gravitational force in this direction, which is mg cosine theta. Theta is angle between vertical and this pendulum. We know what is normal acceleration in this case. That will be v square over r. And v square we can find from energy conservation. So we have kinetic energy in this point equal to change of potential energy, which is mgr multiplied by cosine theta. Now we can count what is v square from here and put it in this expression for acceleration, and we have normal acceleration equal to g multiplied by cosine theta. From the first equation we can find what is tension. Tension will be 3 mg cosine theta, and the maximum for this tension will be when cosine equal 1. It means that the angle is 0, and we have answer D, T maximum equal 3 mg. That was solution for problem number 6. Problem number 7. The following graph shows the results of measurements of two physical quantities, y and x. What is the following best describes the functional dependence of y on x? Below, a and b are positive constants. Solution for problem number 7. The plot shows a linear relationship between x and logarithm y, which means that y is an exponential in x. Since y decreases as x increases, we have logarithm y equal a minus bx, and y equal a multiplied by exponent in power negative bx. That will be answer E. That was solution for problem number 7. Problem number 8. A block of mass m is placed on a wedge of mass m inclined at an angle theta to the horizontal. The coefficients of friction between the block and the wedge and the ground are high enough for both the block and the wedge to remain static. What is the magnitude of the friction force of the ground on the wedge? Solution for problem number 8. Gravity exerts a force mg downward on the block, which means that the wedge must exert a force mg upward on the block. Thus, the block exerts a force mg downward on the wedge, and gravity also exerts a force mg downward on the wedge. Since these forces have no horizontal components, no friction with the ground is necessary to keep the wedge static. This is answer E, and that was solution for problem number 8. Problem number 9. A person is holding a massless rope on which hangs a mass m as shown at left. To pull the end of the rope with a constant upward velocity v, the person must exert a force Fv. To pull the end of the rope with a constant upward acceleration a, the person must exert a force Fa. Now the rope is wrapped around a fixed massless pulley, and the mass is doubled to 2m, as shown at right. Compared to the original setup, how does the forces Fv and Fa needed to pull the end of the rope with a given upward velocity and acceleration change? In both cases, ignore friction and air resistance. Solution for problem number 9. To pull this mass m with a constant velocity, we need to exert force equal mg. To pull this mass with acceleration a, we need to use force Fa equal m multiplied by g plus a. Now let's check what happened on the right picture. Here, to pull this mass with a constant speed, we need to exert force Fv prime calculated from this equation, because now force Fv prime is applied to both ends of this rope. It means that the total force applied to mass 2m equal 2v prime, and that's equal to 2mg. And to pull this end with acceleration a, we need to pull this mass with acceleration a over 2. It means that now we have doubled force Fa prime equal 2mg plus 2m multiplied by acceleration of this mass, which is a over 2. From here we can find that Fv prime equal mg, which is equal to original force Fv, and Fa prime equal m multiplied by g plus a over 2, which is less than original Fa. So it means that the correct answer is A, and that was solution for problem number 9. Problem number 10. The two ends of a uniform rod of length 2L are hung on massless strings of length L. If the strings are attached to the ceiling and the rod is pulled a small distance horizontally and released as shown, what is the period of oscillation? Solution for problem number 10. The sum of the tension forces on this pendulum act exactly like the tension force on an ordinary pendulum of length L. Thus, the period of oscillation must still be 2 pi square root from L over G. Unlike a physical pendulum, the moment of inertia of the rod doesn't matter because it never rotates about its center. So this is answer A, and that was a solution for problem number 10. Problem number 11. Two identical spherically symmetric planets, each of mass m, are somehow held at rest with respect to each other. Each planet has radius r, and the distance between the centers of the planets is 4r. If a rocket is launched from the surface of one planet with the speed v, what is the minimum speed v so that the rocket can reach the other planet? Solution for problem number 11. We just need to compare potential energies of a rocket on the surface of one planet and right in the middle between planets, because in this point total gravitational force is 0 and the rocket just need to reach this point with the 0 speed. So on the surface of one planet we have potential energy equal negative g small m big M over r minus g small m big M over 3r, where 3r is nearest point to the second planet. So this potential energy equal negative 4 over 3 g mm over r. Now let's count what is the potential energy right in the middle point between these two planets. That will be negative 2g multiplied by mm over 2r, which is just negative g mm over r. And finally we can equalize kinetic energy of rocket to the difference of potential energies. So that will be 1/2 mv square equal p final minus p initial, which is 1/3 g mm over r, and finally minimum speed equal square root from 2gm over 3r, which is answer D, and that was solution for problem number 11. Problem number 12. A pulley is constructed by attaching two concentric cylinders with the larger cylinder having twice the radius. Ropes are wrapped around both cylinders. Mass m is hung from each rope and the system is released from rest. Neglect the masses of the cylinders and the ropes. Each mass experiences both a gravitational and a tension force. If the net force experienced by the left mass is F1 and the net force experienced by the right mass is F2, what is the ratio? F2 over F1. Solution for problem number 12. This unusual pulley is called a windlass. Since the right mass is wound around the cylinder of twice the radius, the right mass has twice the acceleration. Since net force equal ma, we have F2 over F1 equal 2, and this is answer D, and that was solution for problem number 12. Problem number 13. Consider a laptop made of two identical uniform plates, each of mass m over 2, connected by a hinge. The hinge is locked when the screen makes an angle theta to the vertical, as shown, fixing the angle between the two pieces. Assuming the laptop does not slip, what is the minimum force that can be exerted on the top of the laptop in the plane of the page to cause the bottom of the laptop to lift off the ground. Solution for problem number 13. When the bottom of the laptop is about to lift off, the normal force is concentrated at the hinge, so we take torques about that point. If the plates have length L, the net torque due to gravity is this one, which is to the right in this expression, while the torque due to the applied force is FL. Therefore, force equals this expression, and this is answer C. That was solution for problem number 13. Problem number 14. A small block is released from rest on the rim of a fixed, frictionless hemispherical ball. From the time the block is released until it reaches the bottom of the ball, which of the following is true? First, the speed of the block never decreases. Second, the magnitude of the horizontal component of the velocity of the block never decreases. Third, the magnitude of the vertical component of the velocity of the block never decreases. Solution for problem number 14. Choice 1 is true because the block is never moving upward, so its potential energy never increases. Choice 2 is true because the only horizontal force the block experiences is the horizontal component of the normal force, which never points to the left. And choice 3 isn't true because the vertical velocity starts at 0 and ends at 0, so its magnitude must increase and then decrease. So it means that correct answer is C. First and the second are true, and that was a solution for problem number 14. Problem number 15. An egg is launched with a speed v from the ground, a distance d from a vertical wall. If v is high enough for the egg to hit the wall, which of the following could describe the angle theta that maximizes the height h at which the egg hits the wall? Solution for problem number 15. This problem is meant to be solved with limiting cases. When v going to infinity, theta going to 90 degrees. This rules out choices A and E. When v square equals gd, it is just barely possible to hit the wall at all, and the projectile must be launched at angle theta equal 45 degrees to do this. This rules out choices C and D, leaving choice B. We have other way to solve this problem directly. For that we need to write kinematic equations for distance and height. That will be these two expressions. From the first equation we can find what is time t and put this time to a second expression. So we have a height equal this expression, which is a function of angle theta. Now to find what is the maximum of this height, we need to take first derivative by theta and equalize it to 0. That will be this expression. And from here we can easily find what is tangent theta. We have tangent theta equal v square over gd. That's answer B, and that was solution for problem number 15. Problem number 16. A hexagonal pencil of a uniform density lies at rest on a horizontal table. It is pushed horizontally with a steadily increasing force halfway up its height as shown. What is the minimum value of the coefficient of static friction between the floor and pencil? so that the pencil will eventually begin to roll. Solution for problem number 16. If the pencil is about to start rolling, the normal force on it will be concentrated at the far end of the pencil. Taking torques about this point, the torque of the applied force must balance the torque due to gravity. If the pencil has a side length r, then this implies equation mg multiplied by r over 2 equal fr multiplied by sine 60 degrees, which will give us force F equal 1 over root 3 multiplied by mg. From other hand, for the pencil to be able to roll, the pencil must not be slipping at this point, which implies force F less than mu static multiplied by mg, and this both giving us mu static greater than 1 over root 3. This is answer D, and that was solution for problem number 16. Problem number 17. A thin rod has a non-uniform density. It is mounted on an axle passing perpendicular to it through its center of mass as shown, and is then rotated about the axle. The axle divided the rod into two parts, one on each side of it. Which of the following must be true, no matter how the mass in the rod is distributed? Solution for problem number 17. For simplicity, let's suppose the rod is made of discrete masses, so the reasoning is exactly the same if the rod is continuous. By the definition of the center of mass, if Ri is the distance of mass Mi from the center of mass, then we have next relation between left and right. The total mass will be next expression, momentum will be this expression, angular momentum will be this expression, and the kinetic energy will be this expression. If we look at these expressions, only the momentum P has the same sum of the same form, so the magnitudes of the momenta are equal, and in general none of the other quantities are equal. It means that the correct answer is B, the magnitudes of the momenta of the two parts are equal. That was a solution for problem number 17. Problem number 18. A cylindrical piece of cork of density ρc, height hc and the cross-sectional area AC is in a larger empty cylindrical container of a cross-sectional area AW. Water of density ρW greater than ρc is slowly poured into the empty container. What is the height of the water in the container when the cork starts to float? Solution for problem number 18. First, let's draw the picture. On the picture we have a container with a piece of cork and water where this piece is just start to float. According to Archimedes' principle, the weight of the water displaced has to equal the weight of the cork for the cork to start floating. If the height of the water in the container is h, then the weight of the displaced water is expression on the left, which is hc/ac, that's volume, multiplied by ρc, which is mass, and multiplied by g. And that's equal to h ac ρw g. After that we can find what is h. So height of the water must be equal to this expression, which is answer B, and that was solution for problem number 18. Problem number 19. A toy elephant is standing on the bottom of a fish tank. The fish tank is filled with water to a depth of 10 centimeters, completely covering the toy. The elephant's legs are perfectly polished, so that there is no water between the bottom of the legs and the tank's floor, and the total area of contact is 0.16 square centimeters. The water has density ρ equal 1000 kilograms per cubic meter. The toy has uniform density 2 ρ. The atmospheric pressure is 10 power 5 Pascal, and the toy has a total mass 120 gram. What is the total hydrostatic force that the water exerts on the toy? Solution for problem number 19. If the elephant's legs weren't perfectly polished, then the buoyant force would be equal to the weight of the water displaced. Since the elephant's density is twice that as water, the force would be mg/2, which is 0.6 newtons upward. However, since the elephant's legs perfectly contact the floor, they experience no upward hydrostatic pressure. Therefore, we should subtract an upward force F prime equal P plus P atmosphere multiplied by contact area A, which is rho GH plus P atmosphere multiplied by A. Now let's count this. That will be this expression, which is approximately equal 1.6 newtons. And now we can count what is the total force. That will be F minus F prime, which is negative 1 newton. It means that this force is 1 newton down. This is answer A, and that was solution for problem number 19. Problem number 20. A bead is threaded on a frictionless wire and launched horizontally from height h with the speed v0 as shown. If the shape of the wire is a step, as in curve 1, then the normal force from the wire on the bead will point inward. If it is shallow, as in curve 2, then the normal force will point outward. There is exactly one possible shape of wire, shown as a dotted line, for which the normal force of the wire on the bead is always equal to 0. What is the horizontal displacement d of the bead when it travels along this wire? Solution for problem number 20. If the normal force always vanishes, then the bead is only experiencing gravity. In other words, it behaves just like a projectile, and the corresponding shape of the wire is a parabola. The bead travels for distance d equal v0 multiplied by time t, and time t we can find from equation for free fall. That's h equal 1/2 gt squared. From here we can find that time t equal square root from 2g over h, and finally distance d equal v0 multiplied by 2g over h, which is answer B, and that was solution for problem number 20. Problem number 21. A cork floating in a cup filled with viscous fluid is placed in an elevator. Below is a plot of the velocity v of the elevator as a function of time t. Which of the following plots best describes the height h of the cork and the cup as a function of time? Assume that the fluid is viscous enough to dampen all oscillations, that the fluid does not slosh as the elevator accelerates, and that both the cork and the fluid are incompressible. Solution for problem number 21. By Archimedes' principle, the fraction submerged only depends on the ratio of densities between the cork and the fluid, so the answer is E. The statement of Archimedes' principle is that the buoyant force is equal to the weight of the water displaced, and the cork floats when its weight equals the buoyant force. The elevator's acceleration affects the buoyant force and the cork weight equally in the non-internal frame of the elevator. Both forces are weights, so the fraction submerged does not change. That was a solution for problem number 21. Problem number 22. A block of mass 2m is placed symmetrically on two identical wedges of mass m as shown. All surfaces are frictionless, and the wedges have angle theta to the vertical. If the system is released from rest, what is the downward acceleration of the block? Solution for problem number 22. In this problem, it's not easy to make forces approach to solve this problem, because point of contact is infinitesimal, and it's not easy to find what is the direction of forces between these masses. But here is better to use energy approach. Suppose that block 2m moves to height h downward. So in that case we can find that change of potential energy equal to 2mgh. And this potential energy converting to kinetic energy of all three blocks. Suppose that after that speed of block 2m is v. Using trigonometry we can find that horizontal speed of blocks m and m are v1 equal v multiplied by tangent theta. So from energy conservation we can write that 2mgh equal mv square plus mv1 square. And using this relation, that will be this expression or this expression. So it means that v square equal 2gh cosine square theta. But from other hand, we know that during motion with the constant acceleration, we have relation between speed, acceleration, and distance like this. V square equal 2ah. It means that acceleration a equal g cosine square theta. This is answer E, and that was solution for problem number 22. Problem number 23. For objects moving through air, the force of air resistance can be modeled as proportional to the speed, linear drag, or proportional to the square of the speed, quadratic drag, depending on the circumstances. Two identical objects A and B are dropped from the same height h simultaneously, but object A is given an initial horizontal velocity v. The objects hit the ground at time ta and tb. Accounting for air resistance, which of the following is true? Solution for problem number 23. For linear drag, the horizontal and vertical components of the motion are completely independent. So we have AX equal negative BVX and AY equal negative G minus BVY. So it means that for both cases we have same vertical equation, and it means that TA equal TB. For quadratic drag we have acceleration AY equal negative G minus B Vy multiplied by absolute value of V. It means that in case A we have a greater air resistance, and it means that TA greater than TB. That's answer C, and that was solution for problem number 23. Problem number 24. A satellite is in orbit around a planet of mass big M. Its maximum distance from the center of the planet is d, and at this point it is traveling at the speed of v equal 1/2 multiplied by square root from gm over d. What is the area of the satellite's orbit? Solution for problem number 24. This problem could be solved using two main properties for orbital motion. First, it's about connection between total energy and the semi-major axis, and second is third Kepler law, connecting period of motion with semi-major axis. So first let's count what is total energy. In furthest point, it's equal to kinetic energy 1/2 mv square, the potential energy gmm over d, which is equal to negative gmm over 2a, where a is a semi-major axis. So here we can use expression for velocity for speed v, this one, put it in this equation and find that semi-major axis could be counted using d. That will be 4 over 7d. Now let's use third Kepler law. From this law we can write that period equal 2 pi multiplied by square root from a cube over gm, and here we can put expression through d. It will be this one, and finally we can count what is the area of this ellipsis. According to the second Kepler law, satellite sweeps the area with a constant speed. It means that this speed equal 1/2 distance multiplied by speed in the furthest point, which is 1/4 multiplied by square root from gmd. And now we can count what is total area. That will be this constant rate, delta A over delta T multiplied by period. And after calculations we will get this expression, which is answer B. That was solution for problem number 24. Problem number 25. A cylinder is placed with its axis vertical, and the rubber band of mass M and tension T is wrapped horizontally around it. What is the minimum coefficient of static friction μ between the rubber band and the cylinder such that the band will not slide down the cylinder? Solution for problem number 25. Let's consider small piece of rubber band on this picture. Suppose it takes a small angle theta, and we can write equation for horizontal equilibrium of this piece. So it means that projection of this two tensions T on vertical must be equal to normal force, which is normal force equal to T multiplied by sine theta over 2, which is for small angles approximately T multiplied by theta. From other hand, we can find what is force of friction. That will be mu multiplied by this normal force. For equilibrium, we have mass of this piece, which is m multiplied by small angle theta over 2 pi multiplied by g. That must be less than mu n, which is mu t theta. And from here we can count that mu must be greater or equal to mg over 2 pi t. It means that this is the minimum for coefficient of static friction. That's answer A, and that was solution for problem number 25.